Hello, Mr. Claudy here, and today we have our final lesson of IB Math SL. Wow, what a journey it's been. And what a way to end it, with two of our least favorite topics combined together, trigonometry and integration. So this will be a challenging but a good review of all the things we've done with trig and all the things we've done with integration. First of all, what we're doing today is we are integrating. Remember, integration is kind of the inverse or the undoing of the derivative. So when I say find the integral of sine, I'm saying the derivative of what gives me sine? Well, the derivative of cos gives me sine, but look, the signs are reversed. So essentially then the integral of sine x is negative cos x. Again, it's a pretty straightforward property. Oh wait, plus c. Don't forget that. For an indefinite integral, there is a constant that could occur. Now the integral of sine, or of cos, is sine x plus c. How do you remember these things? Well, I mean, your formula sheet has the derivatives on it. Let me just get that out here. The formula sheet has all your derivatives, including the derivatives of sine and cos. Remember, tan is not part of the course. And on the next page, it has some standard integrals, including the integrals of these two trig functions. So you don't need to memorize them. But if you were the memorizing type, I always remember, like, well, sine is the first thing I ever learned. So sine is like kind of, I always think of it's like the first child, like the big brother, and they get everything their way. So the derivative of sine is cos. Of course, it's going to be positive. Whereas, the second one I learned, cos, well, things don't always work out as well. So for the second child or the little brother, and the derivative of cos is negative sine. It's unfortunate. But then with integration, the situation's reversed. Finally, the integral of sine doesn't get its way all the time. Here it's getting the negative, and cos finally gets its time to shine, and it gets a positive. Anyways, that's my goofy way of remembering that. But you have your formula sheets if you forget. Okay, that's our lesson. Now we're just going to apply this and revisit all the things that we've ever done with integration, which I'm sure is going to cause some nightmares. So first of all, let's find this integral of 5 sine x. Well, luckily 5 kind of comes out, right? This is something we're comfortable with. So this is really just asking for the integral of sine x, which is just cos x. Well, so this is negative 5 cos x plus c. So that's easy enough when I have a constant out front. I wish that happened more often. If I had a constant inside, though, there's almost like a chain rule here, right? If I was taking the derivative of this, I would take the derivative of cos whatever, but then I'd have to take the derivative of the inside function. Now, the derivative of 3x is just 3. So questions like this with chain rule in reverse, we can do if the interior function is linear, if it's just a constant in front of x. The way I recommend to solve these is to say, okay, leave some space. What is the integral of cos something? Well, it's sine something. So I'm going to write sine something. Now, if I were to take the derivative of this, it would be, the derivative of sine is cos, so I'd have cos 3x times 3. But unfortunately, there is no 3 here. So I do need to put an extra function in front to undo that 3. An extra constant in front to undo the 3, 1/3. If you try it now, what's the derivative of this? It's 1/3 cos 3x times 3, and the 3 and the 1/3 cancel out. If you wanted a rule to help you remember this, basically you take whatever the constant is here and you put 1 over it in front of your answer. But I think it's useful to be able to reason it through. Okay, what do we have here? This looks like a definite integral. Definite integrals are integrals where they have bounds with the integration sign. So the integral from 0 to pi by 2. When we have an indefinite integral, like over here, I have to put a plus c. But for here, I won't. Actually, my answer here will be a numerical value once I sub in these bounds. Let's see if you remember how to do this. I'm going to factor out the half just to make this a little bit easier on me. So what's the integral of sine x? Well, it's negative cos x. So this is going to be half. And then I have like this curly bracket where I write my antiderivative, which is negative cos x. And then I have pi by 2 and 0 as my bounds. Now I can sub them in using the fundamental theorem. So I have negative cos pi by 2 minus negative cos 0. That gives me half. Cos of pi by 2, that is cos of 90 degrees, which is 0. So that's going to be 0. Cos of 0, on the other hand, is 1, so this is going to be plus 1. So my answer is just half. Definite integrals have a numerical answer. Indefinite integrals have an algebraic answer. Definite integrals, you could solve this using your calculator. Now, I just showed you if you didn't have access to a calculator. Okay, let's keep going. What about this one? Integral of sine. Okay, so the integral of sine something is negative cos of that something. And then I need to also have the 1 over this value. So 1 over 4. Negative 1 over 4. Do you want to test it? Well, the derivative of cos is sine of this, then times the derivative of that, which, or sorry, there's a negative, and then derivative of this is just 4. So then that cancels out with the 1/4. Okay, next question. Uh-oh, we have a problem here. We have something that scares me because look, I have what looks like a product rule question. A question like this where it looks like there's a product rule. Remember, I don't have at this point in my studies some sort of way of undoing the product rule, of doing product rule with integration. So sometimes you can solve these questions by inspection, by just looking at them, because it always will work out. The derivative of the interior function will just happen to be this. Otherwise, you wouldn't be able to do the question. But a surefire way of making sure you do this properly, in case you have trouble doing it by inspection, is to use substitution technique. For the substitution technique, we have to set u equal to the interior function, which is 3x to the power 4. If you remember this strategy, now I take the derivative with respect to x, so that's going to be 12x. Then, 12x cubed, sorry. Then I cross multiply and I get 12x cubed dx. Now, what I'm trying to do is replace this so it's all u's. So now I'm going to have cos u. The x cubed and the dx, those two things are here. Well, I have to get rid of this 12 if I'm going to do a direct substitution. So if I divide both sides by 12, now I have my direct substitution. Du divided by 12 is equal to x cubed dx. So now let me replace everything here. X cubed dx, I replace that with du over 12. And this is cos 3x squared. So cos u, and then I have du over 12. Or if you want, I can pull that constant out. So I have integral of cos u du. Look how perfectly this worked out. It just so happened that the derivative of the interior function happens to be x cubed. There was a constant that was a little messy, but now look, I have a really easy integral. The integral of cos u is sine u, so I end up with 1 over 12 sine u plus c, of course. And now you can sub back in u, so you get 1 over 12 sine 3x to the 4 plus c. Now maybe you could have figured that question out by inspection, right? Like I said, it's likely that this just happens to be this, so you could have just guessed sine 3x to the power 4. You would have been really close, you would have just been off by one constant. You might have figured out the constant by a few trial and errors, or you could use the substitution method. Finally, let's come to our last question. I have, oh my god, another definite integral. Well, to do this, again, I'm going to write my antiderivative inside these curly brackets. So what's the antiderivative here? Well, it would be x squared. I'm going to add 1 to the exponent, and then this would be 4, because that's how I would get the 8. The integral of cos is sine. And now I have some bounds to sub in. Okay, well this gives me 4 times pi by 2 squared plus sine pi by 2 minus 4 times 0 squared plus sine 0. Okay, let me clean this up a little bit. I have now 4 pi squared over 4 plus sine of 90, which is just 1, minus 0, minus sine of 0, which is 0. So I end up with pi squared plus 1, which is a nice answer. It's a numerical answer. So these two here are called definite integrals. If you forget about this, you can go revisit these lessons in your integral chapter. Okay, so that's kind of the meat and potatoes of integration. That's probably what the first 3 lessons we did in integration. Then we started looking at some of the applications of integration. So this will be a really good review for us to remember. There's two times you'll use integration, 2 types of application questions. The first is finding the area between 2 curves. If you remember this, it is the area is equal to the integral from a to b, whatever the interval is, of the upper function, or y1, minus the lower function, or y2, or whatever we called it. But that's, conceptually how I do that. In terms of, and then the other application we just dealt with, that is motion. And we, just to kind of quickly write this again, we have displacement, velocity, and acceleration. If you take the derivative, you can go from displacement to velocity, then velocity to acceleration. If you go backward, if you want to go backwards, you have to take the integral. So that's another application. Okay, now let's do some of those application examples. So let's do this first one. Write an expression for the area of the region bounded by y equals cos 2x and y equals cos squared x, where x is between 0 and pi. So here's my diagram. Now how do you know which one's which? Well, cos squared x, remember this is cos x all squared. So whatever y is always going to be positive. That's how it's pretty clear to me that this upper curve is cos squared x, and this lower curve is cos 2x. So if I want to find the area of the shaded region, I'm going to use that strategy that I just had up here. I'm going to take the integral from 0 to pi, because that's where this point was, I guess. Assume it's pi. And then I take my upper curve, which is cos squared x, and I subtract my lower curve, which is cos 2x. Great. That's my expression for the area. That's an amazing application, and that was the big application we learned in our grade 11 course. Shall we solve this? I mean, if you have your GDC, you could plug it into your GDC. But what if you don't have your GDC? It's actually a pretty challenging integral. Because here's the problem. Cos squared x, we can't really take the integral of it. So let me just show you this over here. Cos x squared dx. We cannot solve this. Or we cannot solve this as written. Think about it. The integral with this would involve chain rule. There would be a 2 coming down, cos x, and the derivative of the interior function. It would get a little bit messy. So what we need to do is rewrite this first term, the cos squared x, as some other way that allows me to actually take the integral. Because remember, with the integral, I'm very limited. There aren't that many ways I can solve an integral. So a hint to help you with this is to go back to your trig identities. Let me just open up my to my trig identities. Is there any way I can get rid of a cos squared? Well, I could get rid of a cos squared by using this identity, but then I end up with a sine squared, which is no better. No cos squared, sine squared. Oh, there's one. Cos squared and cos 2 theta. By using this identity, I can transform, I have to do some manipulation, but I can transform a cos squared into a function with cos 2x, which would be a lot easier. Let's write that out. We can rewrite this integral using the trig identity. Watch this. So I have cos 2x is equal to 2 cos squared x minus 1. That's the one from my formula sheet. Now I have cos 2x plus 1 equals 2 cos squared theta. So now cos squared theta is equal to cos 2x plus 1 divided by 2. That's very neat, right? So now I can sub that in. I'm gonna put a little bubble around this. Okay. So now I'm going to rewrite this as the integral from 0 to pi of cos 2x plus 1 over 2 minus cos 2x dx. Now, finding the integral of both of these is now doable. It's a little bit messy because I have cos, why don't I simplify a little bit? So I have cos 2x over 2 plus 1 over 2 minus 2 cos 2x over 2. So I'm just getting a common denominator there. So now I end up with the integral of 0 to pi of negative half cos 2x. Is that right? I have 1/2 minus 2/2, so negative half cos 2x plus half. Okay, now let's find this integral. So I end up with negative half. The integral of cos is sine, right? So that's going to be sine 2x. There's an extra half in front because of the constant here. If I took the derivative of sine, it would be cos 2x and then 1 over 2. And the integral of half is half x. So now let me sub all these things in. So I have negative 1 over 4 sine 2 pi plus half pi minus negative 1/4 sine 0 plus half 0. So my final answer ends up being, okay, well, what is sine 2 pi? That's 0 plus half pi. Sine 0 is 0 and 0. So whatever. So it ends up being pi by 2. Whew, what an ordeal. But it is worthwhile to see how sometimes for a difficult integral, or an integral with a trig that identity has been, or trig ratio has been squared, you actually have to use the a trig identity to rewrite. Now, if you were on a paper 2 test, it would be a lot easier to solve this. You would just use your calculator. You would press menu, calculus, numerical integral, 0 to pi. How do I do pi? Just press this button here. And now we're going to have, should be in rad mode, good. So just to be safe, type this with brackets. So cos x bracket squared minus cos 2x dx. And there we get an answer of 1.5708, which is pi divided by 2. So 2 different solution methods, but this would be a tougher integral, but it's definitely still possible to calculate. Okay, so that is a little review of finding the area between 2 curves. Classic integration thing. For our last problem, our last question, we'll be looking at motion. So I have a particle moves along a straight line, so its velocity is given by this function. When t equals 0, displacement is s. Okay, so this is a boundary condition, right? We know at t0, so should I write that in maybe? I'll write boundary condition. S at 0 is equal to 5. So that's what this is meaning here. Find the expression for s in terms of t. Okay, well, hopefully we can show it to you, but hopefully you remember to find s from v, you just take the integral. So question A is actually pretty straightforward. S at t is equal to the integral of v at t. Notice for this question, there's no bounds to sub in, and we actually want an expression, which means we want algebra. So I'm going to sub in my values, so I have my function, so I have the integral of 4 sine t cos squared t dt. Now this is a bit problematic because again it looks like there's 2 functions. There's a function here and a function here. And we know that I can't take an integral that involves 2 functions. I don't have the product rule. So I'm going to use substitution again. Again, you might be able to do it by inspection, but if not, you always set u equal to the interior of the toughest function. Now this is actually cos, let me rewrite it again. Actually, you know what, I can even take the 4 out. Will I leave the 4 in there? Doesn't really matter. Let's take the 4 out, sure. Integral sine t cos t squared dt. So I can set u equal to the interior function, which is cos t. Now du dt, well the derivative of cos is negative sine t. Now I cross multiply, I get negative sine t dt. So now if I have enough information, can I do the direct substitution? Well, this I'm going to replace with u squared, sine t dt. Okay, I'm just going to bring the negative to the other side. So now I have negative du is equal to sine t dt. Okay, so now I have 4 integral negative du u squared. If I rearrange this a little bit, I get negative 4 integral u squared du, which is a very easy integral. This is going to be negative 4 1/3 u cubed plus c. Don't forget the plus c. So that gives me negative 4 over 3 u cubed plus c. But I'm not done because I have a plus c here and I want a nice expression and I have a boundary condition. Now here's where we have the potential to make some errors. If you were to sub in the boundary condition now, well that boundary condition is in terms of t, right? It's at t equals 0, there it is. And here we have this in terms of u. And I mean, I need an expression in terms of t anyways. So I'm going to sub in back in what u was, which, oh, we decided over here was cos t. So I have negative 4 cos t. I'll leave it in brackets just because we're going to be manipulating it a bit more. Plus c. Okay, so that is not a complete answer because I need to sub in my boundary condition. And that boundary condition is s at 0 is equal to 5. Okay, so let me sub in 5 is equal to negative 4 over 3 cos 0 cubed plus c. Cos 0 is 1, so this is going to be 5 is equal to negative 4 over 3 plus c. So c is equal to 5 plus 4 over 3, c is equal to 5 over 1, so that's 15 plus 4 over 3. That gives me 19 over 3. Oh, I missed all of that. There it is, there's c. So therefore my final expression for s is negative 4 over 3 cos cubed t plus 19 over 3. There it is. What a journey. We can see how when you have a question where you need to find an expression for s in terms of t, that means you can't really cheat and use your GDC. You have to actually do all the algebra by hand. What about part B? Find an expression for acceleration. Well, acceleration is the derivative of velocity. Oh, so that's pretty straightforward. That's just going to be finding the derivative of this. Where can I fit this in? Let's do it over here. So for part B, I have acceleration is equal to the derivative of velocity. So that's going to be the derivative of 4 sine t cos t all squared. This could be problematic as well. So I have to use product rule here. So I'm going to join these two together, and I have, well, let me draw that, write that in. So I have, there's 1 and there's 2. So here we go. Derivative of the first thing is derivative of sine is cos, so 4 cos t times the second thing, cos t squared, plus the first thing times the derivative of cos t squared. So what's the derivative of something squared? Well, it's 2 cos, 2 times that something to the power of 1 times the derivative of the interior function. What's the derivative of cos? It's just negative sine. A little poor space management here. We'll see if I can cram it in. So now I have my derivative done. I just need to clean up my response or my answer a little bit. I have cos t times cos t. So I have 4 cos cubed t. And over here I have a 4 and a 2 and a negative. So negative 8 sine squared t cos t. I'm sure you could factor it or maybe simplify it a little bit more, but that's not really what we're going for at this question. We just wanted to remind you that if you have a a motion question, you could be asked to find an integral or a derivative. It's possible. Both cases are possible. Finally, let's go to question C. Find the displacement of the particle and distance traveled over the interval 0 to 6. Okay, I'm going to do this one down at the bottom. We have two things to find out: the displacement or change in displacement and the distance traveled. Both of these formulas are in our formula sheet under the derivatives chapter. Remember, if you can remember way back, well, actually it wasn't that long ago, we looked at applications in calculus. Distance traveled is the absolute value, the integral of the absolute value of velocity. Displacement is the integral of velocity. The difference between these two things is distance is how much you've actually clocked on your car as you're driving in a circle. You can clock all the actual kilometers that you've driven, Whereas displacement is the difference between where you start and where you end. So if you were to drive in a circle, well, you start and end at the same place, so your displacement is 0, but your distance traveled is actually something. So let's find the displacement. Is the integral of vt dt. The question said from 0 to 6, which is integral from 0 to 6. Where's my function v? 4 sine t cos squared t. So it's 4 sine t cos squared t dt. That's going to be something we do using the GDC. Whoops. So I'm going to take my calculator and I'm going to press menu. I'm going to calculator mode, go calculus, numerical integral, because the answer here is an actual number. Now I have to put in my bounds 0 and 6. What's 6? Did I write that down right? Yeah. 6. Okay, so just a note again about typing trig properly. You're going to type 4. You can't go wrong to put a times here. Now to enter sine, you're going to press this trig button. Make sure you're in radians mode too, which is important because there's nothing here indicating it should be degrees. So you press this trig button and you're going to click sine. And now we're going to put in t. Well, we always use x's, so I'm going to use x. And then I'm going to put times. Again, you can't go wrong with an extra times. And then cos, in this case it's cos x squared. So it's open bracket, trig, cos x squared. And make sure you put the squared in the right place. Be careful that you typed it all incorrectly. You can always put extra brackets and extra multiplication symbols in. You won't, it's better to be safe than sorry. Then you put in the x, type in the press equals, and then you get your answer 0.153. What was this again? It was, I guess it's meters. Yeah, so there we go. That's my displacement. Now my distance traveled is a very similar formula, but it's the absolute value. So this is the absolute value from 0 to 6 of vt dt. You can definitely not do this one by hand. You have to use the calculator. So I don't think I can copy this. Yeah, I don't know how I do. I'm just going to start over. So press menu, calculate, oops, menu, calculus, numerical integral, 0 to 6. Now you might be trying to remember, how do I type in the absolute values symbols? Well, that's a weird function, and the button for weird functions is right here next to the number 9. You click that, there's the one, there it is, it's on the second row on the far left. And now you have those absolute value bars. Now you can type 4 times sine x times, open bracket, cos x squared. And that's dx. Press enter, and there's my distance traveled. It's actually a lot further. So this is another one of those situations. You can see the difference between the two. The displacement between the first in the first 6 seconds. This is a snapshot of where you started versus where you ended. So you're only 100.153 meters to the right. Whereas in that time, you actually went back and forth several times, and you've traveled really far. So your distance traveled is 5.18. Whew, okay. Wow. And that's it. That's the end of our long journey in IB math. Wow. No, don't cry because it's over. Laugh because it happened. You have one last day of homework. There's lots of it. So page 506, number 1 to 12, 508, number 1 to 4, and 512, number 1 to 3. And those last ones are related to motion. And these are all non-GDC apparently. So you'll get some great practice of integrals without using your GBC. Thanks for watching this whole time. I hope you enjoyed, and good luck with everything that comes next, and we'll see you next time.